Hello. So far we've talked about convergence and divergence of series, and we've looked at a number of tests, like the integral test and the alternating series test and the comparison tests, and also the test for divergence. Right? All of them tell us either that a series is convergent or divergent, and based on the form of the series that you have, one of these tests may be more applicable than others. In this video, we'll talk about two types of convergence. Right? So it turns out that given a series, there are actually two ways in which it may converge. Right? So far, what was our definition for convergence? It was that, right, so if you had n equals 1 to infinity, a sub n, you say that that series converges if the sequence of partial sums has a finite value in the limit. Right? So as n goes to infinity. So let's talk about absolute and conditional convergence here. And to begin here, I'll give you two examples of series that we know do converge. Right, so this one and this one. Minus 1 to the n minus 1 n squared. And then minus 1 to the n minus 1 over n. From the alternating series test, these both converge. Right, so this is by the alternating series test. Right, so that's a simple application. You first observe that it is alternating, right, and then you make sure that, okay, do your terms Bn, right, the magnitude of each term, are they decreasing and do they go to 0? So that's true for both these highlighted series, so they both converge. However, if you look at the corresponding series without the alternating signs, you get different behaviors for your series. All right, so let's write out the first few terms. You already know what these look like, right? This is 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared and so on. Whereas this is just the harmonic series, well, the alternating harmonic series here. So they're both alternating and they both converge. Now when you remove the alternating signs and just have pluses for all the signs, well, are they convergent or divergent? You should remember this. Sum of 1 over n squared is still convergent. And remember, we proved this using the integral test. Right, but now we're just going to call it the p-series test, because we already proved that general result about p-series, and here p is larger than 1, so it converges. When p is equal to 1, it diverges. Right, so what's going on there? When we change the signs to be all positive, something different happens for this series and this series. And this is exactly what we'll call a series that absolutely converges, or it has absolute convergence, and a series that conditionally converges or has conditional convergence. Okay, so let's look at the formal statement of the definition. And it's simply this. A series A sub n is called absolutely convergent if the series of absolute values is convergent. Right, so that's quite easy to remember. Absolutely convergent. If you take the absolute values, it's still convergent. Right, so that's exactly what happened with our alternating series 1 over n squared take absolute values of all the terms. Now it's absolute value of minus 1 over 4, so that's plus. So it changes everything to a plus. Still convergent. And absolute convergence is, a stronger form of convergence, right? Because you don't always expect a series to converge in its absolute values if it converges to begin with when it's alternating, right? And that kind of makes sense, because if you look at your alternating series test, right, the bar is really low for a series to converge there. You only have to look at whether your terms without the signs are decreasing and approaching 0. And again, the reason for that is because, well, partial sums are going to alternate, right, around your limit. So this is your limit. The partial sums are going up and down and up and down and up and down. Whereas if your series has all absolute values, then as n goes to infinity, to get your next partial sum, you keep adding terms. You're adding and adding and adding and adding, right? So it's much harder for a sequence to converge in absolute value than for a sequence with alternating plus and minus signs to converge, right? So this is stronger than regular convergence. And if a series is convergent, but then when you take its absolute values, it fails to converge, right? It diverges. Then we'll call it conditionally convergent, right? And these series are actually quite interesting. It turns out, well, I might do this in class, but when you rearrange the terms of conditionally convergent series, you can actually get different sums from them. I won't do that in this video, but that's a quite interesting result. Let's prove what I said about absolute convergence first, though. If you know that a series is absolutely convergent, right? So that's a stronger condition, I said, which means that it actually implies that the series is just convergent, period. Right? So just plain old convergent, if you know it's absolutely convergent. And you may be thinking, isn't that obvious? You have convergent in the name, clearly it's convergent. Well, no, mathematically, these mean different things. What does it mean if a series is absolutely convergent? It doesn't actually tell you anything about the original series, but it tells you something about the series of absolute values. So, well, here's the proof. Well, if sum an is absolutely convergent, then by definition, it means absolute values converge. The series of absolute values converges. So we somehow want to find a way to relate the series of absolute values to the series of just an, and to show that an converges. So what will a picture look like there? So if you have an, something like that, its series of absolute values will be, well, just everything moved to the positive, to the above the x-axis, right? It's what happens when you take the absolute value of a function. Everything below the x-axis gets flipped. So really, the absolute value of a sub n, and a sub n itself, we can actually get a relationship between the two. In fact, what can we say? Well, an, first of all, is always going to be less than or equal to the absolute value of an. Right? So that's pretty clear here. If an is positive, then an is equal to absolute value of n. But if an is negative, then the absolute value is greater, because the absolute value is positive. But then I also have a lower bound for an. It's the negative of the absolute values. Right? So its counterpart down here. And so how am I going to use this now? Well, it kind of looks like I can compare the series, right? Using a comparison test. Because this inequality actually gives me the correct direction to use a comparison. On the right, I have something that converges. And on the left, I have something that's smaller. Therefore, that should converge. Aha, but wait. Remember that to use the comparison test, we need your series to be positive series. We need their terms to be positive before we can compare them. Also, let's make the terms positive. Let's add absolute value of a sub n to everything here. Okay, so now both of these are positive series. And 2 times the absolute value of an, that's also a convergent series, right? From the properties of series. It's just a scalar multiple of a convergent series. So since series 2 times the absolute value converges, but the comparison test the series a sub n plus absolute value of a sub n also converges. Aha, so we're close. In the end, we want absolute value, no, not the absolute value, we want the regular series, sum an, to converge. Well, now we know an plus absolute value an converges, and we know this part converges as well. So what I'm going to do is just subtract. Because if you have 2 convergent series, and you add them, or subtract them, you get something convergent as well. And this finally proves what we need. Therefore, absolute convergence implies convergence of a series. All right, so that's a nice proof there, using a comparison test. So one question I'd like you to think about is this next one. How can we prove whether this is absolutely convergent, conditionally convergent, or divergent? And note here that we're not just asking convergent or divergent anymore, right? So there are more than 2 possible answers now. There are 3. Either it's divergent or it's convergent, in which case there are 2 types of convergence, and you have to decide which one it is. And I just want to note here that this is not an alternating series. So it's sine of n over n squared plus 1. It's not alternating because if you look at the terms down here, these green triangles, so okay, went down, so this is like positive, now it's negative, still negative, now it's positive. Right, so the pattern is irregular there. It's not just plus, minus, plus, minus, plus, minus, right? It's plus, 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 minus, 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 plus, 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 and so on. So think about this on your own time and try to see whether you can prove it's one of these.